I welcome you all for a course on digital signal processing. In this course, we shall look at some of the applications of digital signal processing in terms of filter design, in terms of complex analysis of signals, and to achieve those things we would be requiring to go through a fundamentals of the signal processing, especially the Fourier transform, that is discrete Fourier transform. We will be looking at these in first few modules, and then the filter design will be taken up later. The modern world is bestowed with the sophisticated systems which can perform the complex tasks in DSP, that is digital signal processing, because of the advances in VLSI. The programmable operations which are possible have made the applications of DSP widespread. We will be looking at some of these in detail in the ensuing course. But first, let's look at what this analysis of a signal means. Let us recall that a signal is an entity which carries information. This information is to be extracted by a system, and hence the process of extracting this information and usage of that in further stages constitutes a signal processing task. It can be very mundane task of recognizing a face or a fingerprint, and from that to various other complex applications, for example detection of nodules on a chest X-ray and so on. It can give rise to a variety of applications all around us which knowingly or unknowingly we are using. Such applications are all the basis for which the course on digital signal processing becomes more interesting. Let's recall that a continuous time domain signal, for example x of t, will be sampled and converted to x of n. So this is after sampling, and whenever I say sampling, you must recall the Nyquist criteria for sampling this signal, which says that the sampling frequency should be at least twice the maximum frequency that is present in x of t. This signal, when we obtain, that is x of n, when we obtain this particular signal, is the input to a system. This will be input to the system. The system is expected to process the x of n, not x of t. It will process x of n and extract the information. So this can be done in two ways. That is, one is in the time domain, the other one is in the frequency domain. The processing of the signal, as I said, if it is in time domain or in frequency domain, has their own unique advantages and disadvantages. But some of these operations, which can be just the addition of signals, subtraction of signals, and so on, and it can be other operations which are either performed on the independent variable or it can be performed on the dependent variable. Independent variable is the time, and the dependent variable is the function of that independent variable, like x of n. So I can write here n as the dependent variable and only n as the independent variable. So these operations which we will try to do are mostly in the time domain. The fundamental interest in the DSP will be a set of operations in the frequency domain. It has its advantages and thus we come across a very important tool called as the discrete Fourier transform for the processing of the signal, analysis of these signals. We shall look at the DFT in more detail in the ensuing sections. The time domain signal x of n can be represented in the frequency domain as x of omega. Pay attention to the nomenclature here. The time domain signals are usually represented using x of n, the small case x, and the frequency domain representations are usually done using the capital X of n. So, to perform the frequency analysis on these discrete time signals, so this I can call it as discrete time signal. So, if you want to perform the frequency analysis on such a signal, that is a discrete time signal, we need to convert this to the frequency domain, and the tool that is used in converting the x of n to x of omega is the Fourier transform. So, x of n to x of omega will be done through this Fourier transform, but observe, the same thing can be represented as the Fourier transform of x of n will be the x of omega. Let us also observe the nature of x of omega and x of n. X of n is discrete time. X of n is having samples at n, at varieties of n from minus infinity to plus infinity, whereas x of omega is a continuous function of the frequency. So, this particular aspect, if the learner is paying attention to, then it will be giving rise to varieties of questions in his mind. So, I would like to stress on this particular aspect, that is, the x of omega is a continuous function of omega. X of omega is a continuous function of omega. The important reason why we need the discrete Fourier transform arises from this same fact. Why DFT? The answer to this question lies in the same reason. X of omega is continuous. X of omega is continuous. This continuous signal is not possible to be represented using a modern day computer. The modern day computer has limited memory, and this continuous signal is not possible to be represented using these systems. If the representation is not possible, obviously the operations can also not be performed. So, we need to take samples. Therefore, we will take samples of x of omega. The moment you take samples of x of omega, you will get a finite set of samples, and further this samples of x of omega will be processed by the digital systems, digital computers. So, our purpose of converting x of t to x of n and x of n to x of omega is satisfied, because we will be able to process a continuous time signal x of t using only the samples of the Fourier transform. The samples of Fourier transform are known. You can, in general parlance, as discrete Fourier transform. Samples of x of omega. These are the samples of x of omega which will help us in still processing the original signal and extract the information. So, I would like to in this section, let us look at the possibility of the frequency domain sampling and the reconstruction of the original signal. That is it possible to get x of n and from that obtain x of omega, and from x of omega is it possible to get back x of n? If we are able to do this transition from time domain to frequency domain, then we can rely on this tool. Of course, it has been proved. Let us look at this in more detail. The x of n that we are going to work with is a discrete time signal. It is also an aperiodic signal. That means it is a non-periodic signal. This non-periodic signal is obviously not going to repeat its pattern even after infinite time. And the energy, it is an energy signal. That means it is a finite duration signal. So throughout the course on digital signal processing over here, we will be considering the x of n to be a discrete time, aperiodic energy signal. And when I obtain the Fourier transform of x of n and I obtain the x of omega, it is evident that the x of omega is always periodic. So this is a very interesting concept in its own. Always we know that the Fourier transform is a periodic representation. The given signal x of n is non-periodic, but the Fourier representation is periodic. This itself paves way for reducing or simplifying the complex analysis of the signal. On the screen, if you can see, I have represented the Fourier transform x of omega as a function of omega, So you can observe that the signal is periodic. If I were to consider one period, that is from 0 to 2 pi, all the information that is present in this range of 0 to 2 pi is just sufficient for the complete representation of the signal. The Fourier transform is given as x of omega is equal to summation x of n e raised to minus j omega n is equal to minus infinity to plus infinity. This is the representation of the x of n in the frequency domain. You can observe that the variable x of n, the variable n is ranging from minus infinity to plus infinity, and this is our standard Fourier transform or Fourier domain representation. As I mentioned earlier, the signal x of omega, that is the Fourier representation of x of omega, Fourier representation of x of n is continuous. You can observe that over here where the entire representation is having a continuous values for each of the omega, that is from 0 till 2 pi. This kind of representation becomes, as already mentioned, very difficult to be input into a system and then processed. So the way out is to take samples of this spectrum. If we can divide this into equidistant samples and take only one sample from each of this, say for example k equal to 0, k equal to 1, k equal to 2, k equal to 3, k equal to 4, k equal to 5, and so on. So if you are going to take only samples of this, each of this strip of n frequencies, if we can represent it as delta of omega as 2 pi by n. That means if you are dividing this whole thing into n equidistant samples, okay, n equidistant samples, and take only one sample from each of that, then I'll be getting n number of samples. These n number of samples are the frequency domain samples of x of omega. Question that remains to be answered is it possible to have only such n samples and still get the x of n from such n samples, right? So I have been trying to find the frequency domain samples and then reconstruction. So my basic task is finding the samples is not big, but is it possible to reconstruct the original signal? That needs to be answered. Okay, so we shall evaluate the x of omega. We shall try to evaluate the x of omega at those samples, that is 2 pi by n into k. So the this representation needs to be thoroughly understood, where k stands for the sample number. So k equal to 0 means this first sample. So I'll highlight this sample. So this is the first sample, second sample, this third sample, the fourth sample, fifth sample, sixth sample, and so on till the n minus 1 sample, and again nth sample, and so on. So this k represents the sample. I am trying to find out, is it possible to reconstruct x of n using these samples. So now the x of omega is no longer considered, but only the n number of samples of x of omega are being considered. So I will write the representation as summation x of n e raised to minus j omega n, n is equal to minus infinity to plus infinity. Now in place of omega, I will be writing it as 2 pi by n k, 2 pi by n k. So the modified version will be summation x of n e raised to minus j 2 pi by n k n, and of course n is ranging from minus infinity to plus infinity. Observe here that there are infinite number of such samples. Now these infinite number of samples, is it possible to reduce the complexity, where k of course is the index of the samples. Now this summation over here can be further divided into infinite number of sum of such summations, where each of this summation will be containing around capital N. So there are two N over here. This is one N and there is this capital N. this represents the the time, this represents the time, and this represents the number of samples. So you must be very careful while using these nomenclature, these terminologies. Okay, so the small case n is obviously the time. I am looking at the summation, which the previous summation as shown here, having x of n e raised to minus j 2 pi by n kn. This summation, is it possible to be represented as a sum of, as an infinite sum of finite samples? So it is so this, if it is possible, then it can be represented as summation x of n e raised to minus j 2 pi by n kn. N is equal to minus n to minus 1 plus summation same x of n e raised to minus j 2 pi by n kn. N is equal to, the next term after minus 1, it is 0, 0 to n minus 1, and further the summation same thing, n is equal to n, and so on. So you can observe each of these summations that are shown on the screen, each of them have is n number of, that is number of capital N number of terms, each of them. And how many such terms are there? There are infinite such summations. Each of that summation, if we can combine in one simple term or in one simple representation, then it would look something like this. So it is x of 2 pi by n k equal to summation of summations, x of n e raised to minus j 2 pi by n kn. The inner summation is for n is equal to ln to n is equal to ln plus n minus 1. The outer summation is for L is equal to minus infinity to plus infinity. So the learner is encouraged to look at this expression as just an extended expression or extended representation of the previous one. There were infinite number of terms in the, you can see the expression over here is this one. Say call this equation 1. This equation has x of n ranging from minus infinity to plus infinity. What we did is to break it into sum of summations. Each summation has n terms. This has n terms. This has n terms, and like that each of them have n number of terms. All those n number of terms have been represented using the next version over here, which is summation of summations. For different value of L, you can make out that the entire gamut of samples involved in x of n will be considered for evaluating the x of omega or discrete values of x of omega. What is the purpose of all this thing? The purpose of doing this rearrangement of terms will become evident if we were to change the index of inner summation. If I were to change the index of inner summation from n to n minus ln, then there is going to be a lot of useful insights that you can obtain. So we shall write it as outer summation as it is minus infinity to plus infinity. The inner summation is now n minus ln. So n is replaced by n minus ln. So it becomes n equal to 0 to n minus 1. So you can even otherwise assume that ln is taken to the left side, and n is to be replaced by n minus. So here you will have this term represented, n minus ln, and the other is this twiddle factor over here, that is e raised to j 2 pi by n into k, and we know that n is replaced by n minus ln, so I shall write it as n minus ln. Okay, so this is the representation. But one interesting thing is that this particular representation of e raised to minus j 2 pi by n kn, this can be simplified as e raised to, only this term I am just considering, so it is 2 pi by n kn into e raised to minus of minus. So I am just finding the product, e raised to minus of minus, that is plus j 2 pi by n into k into l into n. Okay, so over here this n gets cancelled, and e raised to j 2 pi k l. So if you can observe, both k and l are the integers. Okay, product of these two integers is again an integer. So you will observe that e raised to j 2 pi k n will be of the form cos of 2 pi minus j sin 2 pi, which will result in value of 1. So this whole term over here, this will be equal to 1. So it is possible for me to simplify the representation from all this thing as, it can be represented as x of 2 pi by n k equal to summation. I'll also interchange the order of summation, that is previously we had the outer summation as L is equal to minus infinity to plus infinity, inner one was n equal to 0 to infinity. This time I shall write outer as n equal to 0 to n minus 1, inner summation as L is equal to minus infinity to plus infinity, x of x of n minus ln into e raised to minus j 2 pi by n kn. Okay, you can observe the reason. So this whole highlighted portion, so this portion is anyways now becoming equal to 1. So I am considering that only the remaining portion, that is over here. The learner is required to pay attention to this summation over here, this particular summation highlighted in blue. This summation amounts to, if I were to represent this whole thing as so that is summation x of n, that is L is equal to minus infinity to plus infinity. If I were to write it as xp of n, so what is this xp of n? If I were to represent the term in this blue bracket as xp of n, then we will observe that it is a extended version of x of n. So let us try to substitute L is equal to 0, 1, 2, 3 or minus 1, minus 2. So for if I were to extend that, for L is equal to minus 1, L is equal to minus 1, it will be x of n, ln is there, so minus 1 means plus n, so x of n plus n. Then for L is equal to 0, it will be x of n. Then for L is equal to 1, it will be x of n minus n. Then for L is equal to 2, it will be x of n minus 2n. Okay, and so on. So this goes on and on till the plus infinity, and this is at n equal to 0, and this continues on the other side also till minus infinity. So very interestingly, it can be observed that xp of n is nothing but the repeated copy of x of n, repeated copy of x of n. Okay, so it is continuously it is a shifted and copied version of x of n. So if I consider an example for you, it can be considered this way: 1, 2 and 3. So what is this? This is the x of n that we are considering. This is the time axis n. So this is x of n. Please recall from a few of the previous slides that x of n is a discrete time aperiodic energy signal. So all these characteristics are satisfied in the representation that is shown. Now what was x of n is known, but here we have a new representation called xp of n. So this xp of n is nothing but the repetition of x of n, shifted repetition. So the first term over here is x of n in its location. The x of n minus capital N is x of n itself delayed by a time unit of capital N. Similarly, x of n minus 2n is x of n itself delayed by a time unit of 2 times n. So this, how do we represent over here? So I can show the same thing as xp of n. So the representation will look something like this. So if I were to consider this as the origin, then this is 1 here, this is 2 here, and 3. So this is 1, 2, 3. This is x of n. Then this further is 1, 2, and 3. This is x of n minus n. Similarly, this is x of n minus 2n. Then x of n minus 3n, and so on, so forth. This continues till the plus infinity. And on the other side, I get x of n plus n. X of n plus n means x of n advanced by a time unit of capital N. Similarly, x of this is nothing but x of n plus 2n, x of n plus 2n, x of n minus 2n, and so on. Okay, so we actually began with a representation of discrete time aperiodic energy signal, but the rearrangement and the equation, this equation is pointing to a subtle representation of x of n in a different manner. So that's the reason this highlighted expression of x of n over here is the xp of n, which can be represented as x of n minus ln L being from minus infinity to plus infinity. So the meaning of this representation is that the Fourier transform, though the rearrangement we could do it for the discrete time aperiodic signal, since the xp of n is periodic, right? This is nothing but the periodic representation. We can represent this using Fourier series. Because you know that Fourier series is applied to periodic signals and Fourier transform is applied to a periodic signal. So though I applied Fourier transform over there, it is actually the representation of xp of n. xp of n happens to be the periodic repetition of x of n. Okay, periodic repetition of x of n, and this in turn is allowing us to apply Fourier series on this representation. Okay, so here I'd like to on your screen you can see the representation of xp of n. This representation is possible because the xp of n is a periodic repetition of x of n. Since it is periodic representation, we can represent the whole thing as a Fourier series, where xp of n has been shown to be summation ck into e raised to j 2 pi by n kn. So you can observe the ck. What are these ck's? These ck's are all the Fourier coefficients. Okay. So using these Fourier coefficients, that means obviously the first expression on your screen now is the synthesis equation. So using the Fourier coefficients, that is ck's, and having e raised to j 2 pi by n kn, you will be able to obtain xp of n. So the left hand side of this equation, left hand side of this expression is xp of n. So using all the ingredients on the right hand side, you can obtain the xp of n. Please recall that xp of n is the repetition of x of n. So the ck as shown here are all the Fourier coefficients. So you can obtain the Fourier coefficients. So this is the analysis equation. So you can obtain the Fourier coefficients in this relation. If you pay attention to this whole term over here highlighted using this bracket, you can observe that this whole thing is nothing but the Fourier transform itself, that is summation xp of n e raised to minus j 2 pi by n kn. This happens to be the Fourier transform from our basic discussion. So replacing this as 1 by ck, so replacing it as ck is equal to 1 by n x of 2 pi by n kn, I would like to use this relation back into call this as equation 2. So put it back into equation 2, you shall observe that xp of n is nothing but summation 1 by n x of 2 pi by n k e raised to j 2 pi by n. So here the range of k is from 0 to n minus 1. What is the meaning of the last expression over here? the meaning of this expression is that if you know the samples, that is x of 2 pi by n. So obviously these set of values over here, these values are samples of x of omega. That means if you know the samples of x of omega, then you can get back xp of n. Okay, so what did we begin with? We actually began with the task of frequency domain sampling and reconstruction. So I wanted to know, can I get back x of n if I know x of omega? If not x of omega, you take samples of x of omega and then try obtaining x of n. So yes, we are able to do that now. We will be able to obtain the xp of n if you are given with samples of x of omega. So let us again look at all the terms in this particular boxed element. Here we have 2 pi by nk, which are all the samples, and then there is this e raised to j 2 pi by n kn. Look at all the elements in this. One is a 2, it's a constant, pi is a constant, so this product 2 pi is possible, it's a constant. The number capital N over here is also again a constant, because we have taken capital N number of samples from the frequency domain representation, so that is known to us. Then k is ranging from 0 to n minus 1, and it is having integer values. So k equal to 0, k equal to 1, 2, 3, 4 and so on. So that is an integer value. Again, n is also ranging from 0 to n minus 1. So this value is also known to us, and this whole thing is being divided by this n. So this is 1 by n, right? So all the terms in this summation are known. Since all the terms are known, we can get back xp of n. Okay, so this shows that reconstruction of the time domain signal from the samples of the x of omega is possible. Okay, so let's summarize this whole understanding in the form of a picture over here, in the form of a diagram highlighting the salient things. So we have x of n, and from this you have obtained x of omega using Fourier transform. From x of omega you have taken samples, so you have not considered the entire x of omega, only samples you have considered. And how many such samples are there? There are n number of such samples, and this k will be an index of that n. For example, first sample, second sample, 10th sample, 50th sample and so on. So you have obtained x of k. From this sample, it is possible to reconstruct the x of n. Now from x of 2 pi by nk to x of 2 pi by nk, did we actually get x of n, or was it something else? If you are very attentively, if you are listening, then you will observe that from x of 2 pi by nk, we actually obtained not x of n, but we obtained xp of n, and from xp of n we can obtain the x of n. So this is directly, it is not suggested. This is how we actually obtained. So we obtained xp of n. So what was the relation between xp of n and x of n? So xp of n is nothing but the periodic repetition, that is x of n minus Ln. L is equal to minus infinity to plus infinity. So this periodic repetition has been obtained. Now it is very much clear that if you have xp of n, you can always get back x of n. So how to get x of n from xp of n? How? So it is clear, x of n is xp of n for n equal to 0 to n minus 1, and it is 0 otherwise. Okay, so you can just truncate the whole of this xp of n only over the range 0 to n minus 1. This has been represented in one of the previous diagrams. You can see here that where is xp of n and where is x of n. X of n is situated only in this range. So only this thing is x of n. Only this range is x of n. The rest all are repetition. So if I am given the xp of n and if I want only x of n, then all that you need to do is remove this portion and remove the other portion, retain only the x of n, that is over the range 0 to n minus 1. Okay, so from the entire conclusion of this discussion is that we can take samples of the Fourier transform, and from those samples we can reconstruct the original signal. This will help us in analyzing the signal using something called as discrete Fourier transform, a very powerful tool for the analysis of discrete time aperiodic energy signal.